Hello differential equation students. So let's take a look at how do we continue to solve higher order linear differential equations with constant coefficients that are non-homogeneous type. So in the previous video we talked about basically how do we write the differential equations in the operator form. And we also looked at the relationship between the differential equation, the operator form, and the characteristic equation. And using this, how do we do that? The most important thing is what we talked about, annihilators. And we looked at the general, for how the function that gets annihilated by an operator becomes a solution to the corresponding differential equation. So if you take a look at here, e to the mx gets annihilated by this operator, and therefore e to the mx is a solution to this differential equation which comes off of this operator, right? So we talked about that. So we're going to take a look at some of the few other basic things today in this video, and then we will move on how to solve the non-homogeneous higher order linear differential equations with the constant coefficients. We'll take a look at some examples as well as the process and how does the process works. So before we get that, let's take a look at some basic definitions on a few things that are very, very useful for us. So let's talk about the linear dependence and linear independence. Let's just say if you have two functions, f of x and g of x, right? We say these two functions are linearly dependent. We say these two functions are linearly dependent if you can write one function as the constant multiple of the other. Otherwise, if you cannot do that, then this is a linearly independent. As a matter of fact, we are more interested in the linear independence rather than the dependence. So if that doesn't happen, right, I'm going to say otherwise f and g are linearly independent. All right. Let me give you a couple of examples. Usually we talk about sets being linearly dependent or linearly independent or not. In this case, let's take a look at this one. Let's take a look at this function f of x. Let's just say as simple as x, and g of x is equal to 5x. You see that these two are linearly dependent, LD, linearly dependent, because I can write the f of x, which is x, right? F of x is equal to x, which is equal to 1 over 5 of 5x, in other words, which is equal to 1 over 5 of g of x. So I was able to write down this right here. If I rewrite it in a different color, I have my f of x happens to be 1/5 of g of x, and so therefore these two functions f and g together are linearly dependent. On the other hand, ladies and gentlemen, if you take a look at this function f of x, let's just say this is simply x, and let's just say g of x is equal to x squared, and there is no other way that I can write. It is impossible to write that f of x is equal to some sort of a constant times x squared. It's impossible. So therefore, in this case, the f and g are linearly independent. I'm going to write as a li, linearly independent. So in general, we say this set. If you want to go ahead with the set notation, the function x and 5x, the set is linearly dependent. And if you take a look at this set right here, the x and the x squared are this set is linearly independent. That's pretty much the simple definition of a linearly dependent, linearly independent. What if you have three functions together? The answer is very simple. Again, the idea is if you have three functions, let's just say f, g, h. If you have three functions in a set, right? We say this set is linearly dependent if you can write one function, it does not have to be f, if you can write one function as the linear combination of the other two. If you can do that, then you say this set is linearly dependent, right? If that happens, this is linearly dependent. Otherwise, if it doesn't happen, then it becomes linearly independent. So for example, if you take a look at this set, that is 1 plus x and 1 half plus 1 half and x. That this set is linearly dependent. The reason because I can write the 1 plus x as 2 times 1 half plus x, right? So in other words, what I did here is I wrote it down, my f as 2 times g plus h, 1 times h. If you call this is your f, if you call this is your g, and if you call this is your h, you see that we can write that. Then this set is linearly independent, dependent. This set is right here is linearly dependent because I can write 1 as the linear combination of the other two. On the other hand, ladies and gentlemen, if I give you this set, 1 as simple as this x comma x squared, there is no way I can write 1 as the linear combination of the other two, and so therefore this set, as a matter of fact, is linearly independent. This set is linearly independent. That is the basics of the linearly independent. And why are we not talking about the linear dependence, linearly independence? If you take a look at the solutions, of any differential equation that we talked about earlier, for example, let's take a look at this differential equation, which is y double prime minus y is equal to 0, whose operator form is d squared minus 1 of y equal to 0, whose characteristic equation is, this is the operator form. The characteristic equation is m squared minus 1 equal to 0. So then you have, m is equal to plus or minus 1. If you recollect, I talked about something called fundamental set, right? Which is going to give you e to the x and e to the negative x. If you take a look at these two elements, as a matter of fact, they are linearly independent. These not linearly dependent. This set is linearly independent set. It's not only for this one. If you take a look at any of these that we had earlier in the previous section, any of these we had this earlier. For example, if you take a look at this right here, this right here, this set is linearly independent. If you take a look at this set, that is linearly independent. And if you take a look at this set, that is also linearly independent. And as a matter of fact, it does not have to be even this, right? If you take a look at the third order differential equation, right, this set right here is also linearly independent. If you take a look at the fourth order differential equation, whose solutions happens to be this one, this also linearly independent, linearly independent, and so on. And we have this like a long set. What if this m happens to be this many, right? We have a whole host of this set. This whole host of functions in this set, even that is also linearly independent set. And if you take a look at this one, this also linearly independent set right there. So that's what makes this is very unique, this linear independence. So therefore we can say one of them is not a linear combination of the other. That's why when we write down this general solution, we know that I cannot write this one because this set is linearly independent set. I cannot write this one as a linear combination of two, so therefore I'm going to have this unique, right? Otherwise, if you can write one of them, in this case, for example, if I can write one of them as a linear combination of these three, then this does not make sense because this is going to cover all possible linear combinations. Then this becomes redundant, right? Then it does not make any sense to say this is a 4-parameter family of solutions. Suppose if it's not linearly independent, that means that you can write one function as the linear combination of the other, so this is not really needed, and so therefore I cannot really say this has 4-parameter family of solutions. So that's very, very important for our purposes. So let's take a look at so that is the relationship between the fundamental set of solutions, a linear combination, and the parameter family of solutions. So in other words, what I'm trying to say is, if I have a differential equation whose solution is, if I have a differential equation, I'll just take a look at this one, as simple as this one, y triple prime minus 2 3y prime double prime plus 2 y prime is equal to 0, right? Whose characteristic equation, whose operator form is going to be d cubed minus 3d squared plus 2d of y is equal to 0, and whose characteristic equation, this is the operator form, right? The characteristic equation, which is going to be m cubed minus 3m squared plus 2m equal to 0. And if I simplify, this is going to be m times m minus 1 times m minus 2 equal to 0. That's going to give me m is equal to 0, 1, 2, and therefore the fundamental set of solution, which is what I call the fundamental set, is going to be e to the 0x and e to the 1x and e to the 2x. And by the way, let me simplify this as simply e to the 0x is 1, and e to the 1x, I don't have to say e to the 1x, I can simply say e to the x. And this set, ladies and gentlemen, is a linearly independent set, right? And so therefore, if you take the linear combination of all these three, if you take the linear combination of all these three, the linear combination is what we call the general solution, right? Is what we call the general solution, and which is, by the way, is going to be y is equal to c1, the first one, plus c2 times the second function, plus c3 times the third function, right? And now you have here, because of it's a linearly independent set, I know I cannot write any one of them as a linear combination of the other. I cannot write the e to the 2x as a linear combination of the other. I cannot write the e to the x as a linear combination of the other two. I cannot write one as a linear combination of the two. That's what guarantees this is going to be a 3-parameter family of solutions. As a matter of fact, number of solutions that I have, number of functions that I have in here, that's going to be the number of solution, that's going to be the number of parameters. So we can say that this is a 3-parameter family of solutions. The reason, because this set is a linearly independent set. So that's the relationship between all these three. All right, now let's take a look at how do we solve non-homogeneous higher order linear differential equations with constant coefficients. But before I go there, I want to quickly say one thing, probably we might use it later, and that is about how do we verify whether two functions are linearly independent or not. So there is a nice, which we'll use it later, by the way, so it's a good idea to introduce it right now. So we say two functions are, it does not have to be even two, you can extend it to 2 or 3, 4, right, are linearly independent, right? We can verify if it's linearly independent or not if what we call the Wronskian. So if you have to, let's just say two functions, f1 and f2. So you have two functions, f1 and f2. We say these two would be linearly independent, right? These two would be linearly independent, right? Then what's going to happen is that what we can say is that we can say, if you take a look at this matrix, f1, f2, f1 prime, f2 prime, right? If you take a look at this matrix, and there's a name for this matrix, by the way, and that is called the Wronskian. This is called the Wronskian. Wronskian, right? And let me write it down as a W, Wronskian of f1, f2. If you take a look at the determinant of this matrix, and if this is not equal to 0, then this is going to be linearly independent. If that is equal to 0 for some x, it does not have to be for all x. Even if that is equal to 0 for some x, it will become linearly dependent. It does not have to be two functions. It could be, let's just say, what if I have 3? Or what if I have a 4? Even what if I have an n? If you have n number of functions, f1, f2, f3, all the way up to fn, right? Let's take a look at the Wronskian, right? If you take a look at the Wronskian, which is, f1, f2, up to fn, right? And the Wronskian is going to be this. You're going to have, f1, f2, up to fn, f1 prime, f2 prime, up to fn prime, and then you keep on go all the way up to f1 n minus 1 derivative, f2 n minus 1 derivative, fn n minus 1 derivative. And you take a look at this determinant, which is not an easy computation, it's going to be expensive, but if this is not equal to 0, then we say this set is linearly, then we can say this set right here is linearly independent set. linearly dependent set. If that is equal to 0 for some x, then it becomes linearly dependent set, right? So we can do that. For example, let me quickly verify one other thing so that you can see it. You can see it easily. Let's take a look at this set. Let's take a look at this set, simply 1 and e to the x. If I try to find the Wronskian, ladies and gentlemen, if I try to find the Wronskian, right, of 1 comma e to the x, which is going to be 1 e to the x, 0 and e to the x. Those are the derivatives. And if I do the determinant, you would see that this is going to be e to the x. You know that e to the x can never become 0 no matter what the x is, right? So therefore we can say this set, this 1 comma e to the x, is a linearly independent set. This is a linearly independent set, and again we can just work through that way, nicer way. If you take a look, if you apply this to any of them, right, if you do the Wronskian of this, right, if you try to find the determinant of those Wronskians, that's also going to be non-zero. Anything that we talked about earlier is going to be non-zero there. All right, now let's take a look at how do we solve this one. I'm going to give you a process, and then I'm going to go through the process with you how to do it. Then I'm going to do an example with that particular process. Let's take a look at the process. So let's see how does the process works, right? So before I go to the process, so in this case, we are going to use the annihilators. We are going to use the fundamental set, and we are going to take a look at, a few other things, right? So annihilator and the fundamental set are very important. So in solving non-homogeneous higher order linear differential equation with constant coefficients, right? So this is the process. Suppose you have a differential equation given to you, right? Let me make it up, right? Just say you have some differential equations given to you, that is a sub y of n, or an minus 1 y sub n minus 1 dot a1 y prime and a naught y is equal to some sort of a function, let's just say h of x. So this h of x is what constitutes as non-homogeneous, right? Here we want to make sure that h of x is not equal to 0. If h of x is equal to 0, the life is easy. We can use the the characteristic equation, what my students used to call M&Ms, right? They are easy, so we can do that. Now here we cannot use the M&Ms characteristic equations to solve that because h of s is not equal to 0. So so when you deal with the non-homogeneous differential equation, you're going to do two things. So what are those two things? In general, the general solution, right? This general solution is going to have two components, and that is we're going to call y is equal to yc plus yp. In some books, you might say this is yh plus yp, and this yc is basically a solution to the YC is basically solution to the homogeneous problem. That's why you see the YH in there, right? This is the homogeneous case, and this YP is a solution that is coming out of the non-homogeneous part. That comes out of the non-homogeneous part. So the solution, you're going to have two components, YC and YP. YC, you already know how to solve it. YC is the easiest of all. YP is the little long process that you have to work with. So how do you do that? There are other methods, but I'm going to show you a method that works nicely, wonderfully, procedurally very well. Right? And we call this one as the YC as the complementary solution. That's why we use YC, complementary solution, right? And the YP, as we say, it is a particular solution. We call this the YP as the particular solution, YC as the complementary solution. So now we're going to do two things. We're going to find the YC and we're going to find the YP. Let's take a quick look at how do you find the YC. YC is the easiest of all, right? How do you do that? So before we do that, what I'm going to do is I'm going to show you a couple of things in here. I wanted to rewrite a few things in here so that it's easier for you. The step number one is I want you to write down this differential equation in the operator form. So you're going to have the operator an tn plus an minus 1 t of n minus 1 dot 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 dot, and then a1 t plus a sub 0 of y is equal to h of x, right? That's what you have. And I'm going to call this, if you don't mind, ladies and gentlemen, this, since it looks like a something to the d, I'm going to call this as a function of t. I'm going to call this as f of t. Then I'm going to call the, not this one, the annihilator for this one. Let me use a different color. The annihilator for this one, right? Something that annihilates, right? Something that annihilates. Annihilator of this one, which I'm going to call g of d. G of d. I'll give you in a moment what do I mean by that, right? So for example, let me show you. Suppose if you have a differential equation as simple as this. Let's take a nice differential equation which is as simple as the following. Let's just say I have this differential equation which is y double prime plus y is equal to e to the x, right? As simple as that. Then what I'm trying to say is the step one is going to be, I'm going to be rewriting this as d squared plus 1 of y is equal to e to the x, right? And this is what I call f of d, which is d squared plus 1. And what is my g of d? G of d is the annihilator for this one, right? That is the annihilator, right? And that in this case would be simply d minus 1. So that's your f of d and that's your g of d. So the step one is to write down this way and then identify your f of d and g of d, right? The annihilator of the right hand side, the non-homogeneous part, and the operator form of the left hand side, which is the f of d, right? That's the step number one. We're not going to use it for a while, but that's okay, right? Step number two is what we are going to do is basically we're going to find the yp. We're going to find the yc, I'm sorry, or you can say, if you want to call it as a yh or y cap h or y small h, whatever you want to call it, you can call it too. How do you do that? That's very simple. First you write down the homogeneous version of the differential equation, which we talked about in a couple of videos earlier, right? And then that's basically you take a look at the left hand side and set equal to 0. So you take the whole thing, you take this whole thing and set this one equal to 0, right? So now let me really do it. Let me really copy paste and do it. I'm going to copy this, right? So I'm going to paste it, and then I am going to set, let me change the color so you can see it better. Then I am going to set this side to be 0, right? When I do that, you know how to solve them. Then the next thing what you do is that you find the characteristic equation, right? Next thing what you do is you find the characteristic equation, and then you're going to solve the characteristic equation. That is going to give you m's, m1, m2. In this case, you're going to have up to mn, and then you're going to have fundamental solution set corresponding to that. Which is going to be e to the m1x, e to the m2x, and then it depends on if it's repeating and so on. You're going to have this set, right? But rather than calling f as, I'm going to call f as h. Very, very important, right? Make note of this. I'm going to call this the f as h. There's a reason for that. Why am I calling this f as h? Is that this is the fundamental set that is coming off of homogeneous differential equations, right? So let me change the color. This color doesn't look good. So I'm going to call this is the fundamental set, right? f as h, right? Make note of that h. All right. So now you know how to find the solution. So the yp is simply the homogeneous part. So it's going to be yc is going to be not yp, yc, which is the linear combination of these. What is the linear combination of these? That's going to be c1 e to the m1x, plus c2 whatever that you're going to have, e to the m2x. If it's repeating, if it's a complex numbers, you know how to do them. Then you're going to have a c1 cn e to the mnx. And again, you may not have all the time e's. You may have x times z or x squared times z or e to the alpha times cosine beta and so on. But that's a general idea, right? So you can find the yc that way. Then the next step is the finding yp. So how do you find yp? This is little tricky. So this is where we're going to use the the annihilator, annies, and so on, right? So what we are going to do is the following. So what we are going to do in the next step in finding the yc is that I am going to take a look at the f of d that comes off of this and g of d that comes off of the annihilator, right? So I'm going to make a new differential equation, right? I'm going to say f of d operated with g of d, right, of y equal to 0. Again, remember, this is also it's an operator, it's a differential equation, the operator form, and this is also a homogeneous part, right, because that side is 0. And so therefore we're gonna have a solution to this, right? Whatever that we get the solution out of this, right, the same way that we did earlier, right, you're going to find the characteristic equation and so on, and then I'm going to get a fundamental set of solution. I'm going to call that as a f as in h. This is very, very important. I'm going to call that as a f as in h because that comes off of the g of d. G of d comes off of the non-homogeneous part, so I'm going to call it as the fundamental set that comes off of that is in relation to the non-homogeneous part. So I'm going to call it as a f as in h, right? Then what I am going to do is the next step is the following. The step 4 is I'm going to take a look at the f as in h. I'm going to subtract f as h. I'm going to set subtraction. You all know the set subtraction, right? Then your yp, right? So this set, right? Then your yp, I'm going to call this set as fsp. That corresponds to the particular solution. Your yp is going to be a linear combination of that. But it's not just any linear combination. As a matter of fact, we can find those linear combination constants precisely. What would that be, right? So I'm going to say yp is in this set fsp, which is equal to f as nh minus f as h, right? I'm going to say that. And then depends on number of, let's just say you may have a couple of functions in there, so you're going to have yp is going to be equal to, it depends on number of things that you have. It's going to be alpha 1 some function, right? I'm going to call f1 plus alpha 2 f2. Then you should be able to figure out all these alphas, right? Then you should be able to figure out all these alphas. Once you do that, then you can, now you know your yp, you also know your yc. You put these two together, and that's going to give you the general solution, which is yc plus yp. So therefore the general solution, right, general solution, then y is going to be yc plus yp. Let me give you an example so you can kind of follow what I just did, what I'm going to do, right? But that's the general overall idea in there. One thing I want to quickly emphasize before I solve the problem, the way that we find the solution, the alpha and alpha 2, is that this yp is a particular solution. That means when you plug in this yp is a solution, right? When you plug in this yp into this original differential equation, right, it's going to give you this h of x. It is going to give you this h of x. Remember, this is a yc is a complementary solution, right? That comes out to the homogeneous part. So when you plug this yc into this differential, into this operator, or into this differential equation, right, that is going to give you 0 because that comes off of the homogeneous part, right? That's going to give you 0. So this is going to give you, the yc is going to give you 0, and yp is the one that's going to give you this h of x. The yp is the one that's going to give you the h of x. So that's why when you add these two together, yc and yp gives you 0, and yc gives you 0, and yp gives you h, yp gives you h of x. So that's why you have 0 plus h of x equal to h of x on the other side, right? So that's how this works. So when you try to find the alpha 1, alpha 2, what you're going to have is that you're going to use the fact that the yp is a solution to the non-homogeneous part. So therefore when you plug in then you should have the hfx on the other side. I'll talk about, when you took a look at the example, what do I mean by that, but that's something that, theoretically you should know how before I proceed. So let me give you a simple problem first, and then let me show you maybe another problem on how to solve it. So let me just quickly summarize the process that I had. So what I'm going to do, the very first step, I'm going to write down in the operator form. I'm going to find the f of d and g of d. Then I'm going to find the yc, which is a solution to the complementary solution to the homogeneous problem, also known as the complementary solution, the same way we did earlier. And then the step 3 is to find the yp, which to do that I'm going to operate. You can just say multiply, but really not multiply, but operate f of d with respect to g of d and set it equal to 0. And we're going to find the f as an h, and then we're going to say yp is in f as an h minus f as h, and then we're going to find the yp, the constants of those yp's, using the fact that yp is a solution to the non-homogeneous problem. That's a particular solution, and we do that. Let me quickly solve this following problem. Let's take a look at this problem. All right, let's take a look at this problem. Very simple problem. The problem is y double prime. So I'm going to say solve y double prime minus 2y prime plus y equals e to the 2x. As simple as that. It's not a big deal, right? So step number 1, right? Step number 1, let's write down this as in the operator form. If you rewrite it, right, you all agree with me, right? I'm just going to follow these steps, right, just like that we had earlier. Step number 1 is the operator form. In this case, that would be d squared minus 2d plus 1 of y is equal to 0. Let me identify my f and g. Is equal to e to the 2x. This is my f of d. That's simple. That's very easy. So therefore, that tells me f of d is equal to d squared minus 2d plus 1. What about the g of d? The g of d is going to be is the annihilator for this one, right? The annihilator. And we know that from the ones that we looked at earlier, the annihilator for these ones are, if you take a look at this, right? For e to the mx, the annihilator is d minus mi, and what I have is e to the 2x. So therefore, the annihilator is going to be d minus 2. So this is going to be d minus 2, right? All right. So we did the step number 1. We did this one, right? We found this, we find these two. Step 2 is to find the yc. To do that, what I'm going to do is I'm going to take the homogeneous version of the differential equation. So which is going to be y double prime minus 2y prime plus y equal to 0. Or if you want to say, you can also take a look at the operator form, which is d squared minus 2d plus 1 of y equal to 0, whose characteristic equation is m squared minus 2m plus 1 equal to 0. That tells me m is equal to 1 comma 1. That tells me my m is equal to 1 comma 1. Therefore, the fundamental set, not just fundamental set, fundamental sets that comes off of the homogeneous version, so I'm going to call it as f as h, is going to be e to the x and x e to the x. And so therefore, ladies and gentlemen, your yc is going to be linear combination of these two functions, and these two are linearly independent. So I'm going to have c1x plus c1 e to the x plus c2x times e to the x. And now we are going to find the next step. Next step is to find the yp. Yp is a little long process, but we can do it. So let me change the color. So I have a step 3. Step 3 is to find the yp. So step 3 is finding yp, not finding Nemo, finding yp. What is the yp in here? So to do that, as I said earlier, I'm going to take a look at the f of d. I'm going to operate that with respect to g of d of y. And we already have the f of d and g of d right here, right? We already have the f of d and g of d right here. So if I do that, ladies and gentlemen, what I'm going to have is I'm going to have d squared minus 2d plus 1 operated on d minus 2. Again, my goal is to find the solution to this setting equal to 0, right? Of y equal to 0. To find the solution, I really don't have to do much. I'm just going to write down the characteristic equation right away. If I write down the characteristic equation, you see this is going to be m squared minus 2m plus 1 times the m minus 2. It's already factored, so why do I want to bother, right? This is going to give me m is equal to 1 comma 1 and then 2, and so therefore f as nh, not f as h, not fs, the fundamental set of solution that comes off of the non-homogeneous part is going to be e to the x, x e to the x, and e to the 2x, right? So we got the f as h and f as an h. We are right here, right? We got the f as an h right there. Now we're going to take a look at the step 4, which is yp. Yp comes off of f as h f as an h minus f as h, right? So let's quickly do that. Let me change the color. So step 4, then I'm going to find the yp, right? Yp is in f as nh minus f as h, which is f as nh would be minus f as h, right? Which is going to be e to the x, x e to the x, e to the 2x, minus e to the x and x e to the x. If I subtract this, you remember this set notations, right? So set subtractions, these two will go away, these two will go away, and I'll be left with simply the set e to the 2x. In this case, it's only 1, not a big deal. So therefore your yp, ladies and gentlemen, is going to be equal to some constant alpha times e to the 2x. So I'm almost done, right? I got my yc right here. You can find the C1 and C2 unless initial conditions are given to you, but yp you must find the alpha. You must find the alpha in the yp. And to do that, as I said earlier, I'm going to use the fact that yp is a solution not to the homogeneous version but to the non-homogeneous version. So therefore, if I plug the yp in to this original differential equation, I should be able to get the 2 to the x. That's the idea in solving them. So let's see how do we do that. So the original differential equation is, the original differential equation that we had is, yp double prime. The differential equation that we had was, y double prime minus 2, what did we have here? Minus 2y prime plus y, minus 2y prime plus y is equal to e to the 2x. Since yp has to satisfy this, right, then yp double prime minus 2 times the yp prime plus yp must be equal to e to the x, right? So to do that, let's figure out the yp double prime and yp double prime. We already have the yp, so if I find the derivative, it's a nice function. This tells me my yp prime would be 2 alpha e to the 2x, and yp double prime would be 4 alpha e to the 2x. And if I plug this in, if I plug all these informations back into this differential equation, you would agree with me that I am going to have 4 alpha e to the 2x minus 2 times 2 alpha e to the 2x, because that's a yp prime, plus alpha e to the 2x. I made a mistake here. This is supposed to be e to the 2x, and that is supposed to be equal to e to the 2x. Now let's see if I can solve it. If I simplify this, ladies and gentlemen, you would agree with me this 4 alpha e to the x, and this is 2 times 2 alpha e to the x will get cancelled. My left hand side is simply going to be alpha e to the 2x, and my right hand side is simply going to be e to the 2x, and that tells me my alpha must be equal to 1. Right, that my alpha must be equal to 1, and so therefore let me use a different color in here. Therefore my yp is going to be equal to 1 times e to the 2x. I got my yp and I got my yc, and so therefore, ladies and gentlemen, the general solution is, therefore the general solution, right, is going to be, as I said earlier, y is equal to yc plus yp, and this yc is c1 e to the x plus c2 x e to the x, and the yp is, what I got was, e to the 2x in there. So this is your yp, this is your yc, and this is your yp, and that's how you find the solution to the non-homogeneous differential equation. Let me once again simplify what I just have in here so you can kind of see what's going on. If I simplify what I have in here, ladies and gentlemen, the process is first we find the the f of d and g of d, then we find the yc, which is basically solution to the homogeneous version. Then we find the yp, we do this, and then we get the f as h. We already have a f as h, so we find the f as nh. We subtract the f as h from f as nh, and then we write the yp, depends on what you have. And then you're going to have constants. In this case we had only one in our example, but I'm going to another example where we have more than one. And then the general solution is we put the yc and yp together. That's going to be the general solution, and that's how we solve this particular problem right there. I will stop it right here. In the next video I will go through another example of this problem right there.